Hello everyone. In this presentation I want to present the results of our project on benchmarking surface heat fluxes. And I work together with Jasper, David and Christoph. So the general aim of our project was to develop a tool for benchmarking land surface modules of ECMWF models. And why is it important? Because surface heat fluxes are a very important part of the surface energy balance, and they determine the exchange processes between atmosphere and surface. And there are two types of turbulent heat fluxes. That's the sensible heat flux, which is driven by temperature gradients between atmosphere and surface, and the latent heat flux, which is driven by moisture gradients between atmosphere and surface. And they depend on, for example, orography or vegetation and the moisture availability, also on incoming solar radiation, for example. And in the bottom right plot, you can see exemplarily the seasonal cycle of sensible and latent heat fluxes. And you see that during the summer month, we have positive fluxes, and during the winter month, they are close to zero or also slightly negative. And this means in terms of the sensible heat flux, we have a positive sensible heat flux when we have unstable stratification, and a negative sensible heat flux in stable stratification. And for latent heat flux, the latent heat flux is positive if we have evaporation or transpiration from plants, and negative latent heat flux indicates condensation or deposition. And the status quo was that there's this Python package landware, which allows for validating soil temperature and soil moisture. And we wanted to extend this for the surface heat fluxes. And for this, we use model data and observational data. And for the models, we consider three different kinds. So first of all, ERA5, which is one online, fully coupled with data assimilation and has a resolution of about 31 kilometers and 1 hour. And then ERA5 land, which is one offline driven by ERA5 with a higher resolution, 9 kilometers, and temporally 1 hour as well. And then we use additionally the hydrological forecasting system, which is also one offline and driven by ERA5, but contains an updated vegetation scheme and has a resolution of 31 kilometers, but temporally just 6 hours. And we compare this with eddy covariance measurements. That's the classical type of measurements for turbulent fluxes. And as you can see in the figure, this is a sonic anemometer, measures wind speed in a very high frequency, for example, 20 Hertz. And this is combined then with thermometer and hygrometer measurements, so for temperature and water vapor mixing ratio, which measure as well in a very high frequency. And the portal which provides such measurements is the Integrated Carbon Observation System, ICOS. And this contains all the flux towers in Europe. And these are really point measurements. And they, in the end, are averaged over 30 minutes. Yeah, so we want to compare the model data with the observational data. And for this, we need to do some pre-processing. So first of all, you can see in the figure on the right side, all the ICOS stations in Europe. And for every station, we find the closest model grid point. And then we do some adaptations. So we convert units, adapt the sign convention and the time resolution, and convert the time zones. And important is also that the fluxes are instantaneous measurements, whereas the model data is normally accumulated, so it has to be deaccumulated. And then we apply some simple quality control to find very negative or unreasonable high fluxes. And we also delete incomplete time series. And then we have a time series for the model and the observation. And in our case, we just consider 2020. And for this, we can then apply several validation metrics like the correlation coefficient or the bias, for example. Okay, so I want to show some of the results, exemplarily for ERA5. And first of all, you can see here the diurnal and seasonal cycle of a sensible heat flux. So the left plot shows the model and the right plot the observations, averaged over all stations. And on the x-axis, you can see the month, and on the y-axis, the hour of the day. And we see that the diurnal and seasonal cycle coincide very well. We see these high values during summer and day, and the negative values during nighttime and winter. But we also see that there's a quite big difference in the amplitude. And to investigate this a bit more, we can look at just the diurnal cycle. Here again for the sensible heat flux. You can now see on the x-axis the hour of the day, and in the left plot the linear correlation, averaged over all stations again. And we see that during daytime, we have a very high linear correlation of 0.8, whereas during night and especially in early morning, we have a really low linear correlation of just about 0.3. Whereas if we look at the bias on the white plot, we see that the bias is very negative during daytime, so up to -60 watt per square meter, and slightly positive during night, so 6 or 7 watt per square meter. So this, we can summarize that during daytime, the model is quite good in predicting the diurnal cycle, but also because the fluxes are quite high during daytime, there's a quite big difference. So it's easier to have a big difference if the fluxes are already big. And during night, we have a very low correlation, so the model does not add any on just the bit scale to the diurnal cycle. And the bias is quite low because the fluxes are already low. But here the bias is positive, which means that the model slightly overestimates compared to the eddy covariance measurements. Yeah, so we saw that there's a strong diurnal variability. So we can also look at the daily average of the fluxes. So here you can see, again, the linear correlation and the bias for sensible heat flux. And now you can see on the x-axis the location of the station, so their latitude. And you can see that for the daily average values, we have on average very high linear correlation of about 0.8. Even if it's during nighttime, we just have a very low linear correlation. Just some stations, especially for the southern stations, and latent heat flux sometimes has lower correlations. And if we look at the bias on the right side, we see that the sensible heat flux has on average a negative bias, about -20 watt per square meters. And the latent heat flux on average, the bias is close to 0, but we also see a slight latitude dependence from negative values at the southern station to more positive bias at the northern more stations. So this, we can summarize that the sensible heat flux is overestimated, but the latent heat flux, there we see especially a latitude dependence. Okay, then I also want to look at the flux partitioning. So flux partitioning means to look at the ratio between sensible and latent heat flux. This ratio is sometimes called Bowen ratio, and this is an important dimensionless quantity to describe the climate. So for example, we have a high Bowen ratio if we have more sensible than latent heat flux, which indicates a drier climate, whereas the Bowen ratio is lower if the latent heat flux is larger than the sensible heat flux, indicating a more wet climate. And here you can see on the left plot the seasonal cycle now, the month on the x-axis, and then the sensible and latent heat flux for the ops and the model. So you can see that the sensible heat flux for the ops is much larger than for the model, whereas for the latent heat flux, there are just smaller differences. And if we now look at the ratio on the right side, we see that the ops has for every month a higher Bowen ratio than the model. And the difference is especially dominant during spring and summer. And this shows that the that the model has a lower bone ratio on average, which indicates a more wet climate. Okay, to summarize this first part, we looked at the diurnal and seasonal cycle, and we saw that during day and summer we have a very high correlation, but also high negative bias. So on average, the model underestimates the fluxes. So an example for this is that during convective boundary layers, there are very large eddies, and often their heat transport is underestimated by the model. Whereas during night and winter, we have a low correlation and a slightly positive bias. So the model tends to overestimate the fluxes. And this low correlation, that's a special issue in stable boundary layers. And this is because the turbulence in stable boundary layers is very weak. So it's not a well-developed turbulence. So the turbulence is very intermittent then, and this is really difficult to model. Yeah, we also saw that if we look at the daily average, then we get a high correlation between model and ops. And this additionally indicates that there's a strong dependence on the averaging or accumulation times, which should be considered for the interpretation of the validation of the fluxes. And we looked at the flux partitioning, and there we saw that the ratio of sensible to latent heat flux in the model is lower, which indicates a wetter climate. And now it would be nice to generalize this and have a package that does the validation automatically. And for this, we use Landwehr. And as already mentioned at the beginning, it was developed for soil temperature and soil moisture, and we extended this now for surface heat fluxes. And the idea is that you really call just from the terminal Landwehr and then a name list. And the name list specifies the parameters. So, for example, the used data, the control experiment and the experiment itself, then the time and the resolution, and they are passed through the class. So that's the core of Landwehr, the class LDAS, for land data assimilation. And this name list parameters are attributes in this class, and there are additionally some other attributes. And this class also has several methods. So I just mentioned here the three important ones. So the pre-processed data method, as the name indicates, is for the pre-processing of the model data. And then the method in situ validation is performs the validation of the model versus the in situ measurements and applies all the metrics. And then there's also this method web create, which creates the output. So it summarizes all plots and tables in an HTML file. And this HTML file is the output of Landwehr. And here's an example of this. So you can see that that's summarized in several tables. And you can see, for example, the command which you use to call the validation. Then there's a summary of the used experiments, for example, here ERA 5 and the hydrological forecasting system. And then the summary of the validation metric starts. And here, for example, you see map plots. So then we have one column for sensible heat flux and one for latent heat flux. And here we look just at Europe and have then for both models separately the correlation coefficient and then a comparison. And then we have also part on box plots indicating if the experiment performs better or worse than the control. And this is done by using this Fisher-Debt transformation, which then allows to say if there's a significant improvement of the experiment versus the control. And then there's also part summarizing all the scores and tables. So for the annual score and then for the seasonal scores. And this is separated for every network. Here we just use ICOS. And then there are also more metrics and also some other plots. And here's our examples of these plots. So for example, here the left plot is the map plot. You see Europe and then the station location color-coded depending on their correlation coefficient. Then you can see here bar plots indicating the significant improvement, or if the experiment improved the control or not. And then here's a table summarizing several scores. So you can see this here for our year 2020, and 33 stations were used in the validation, so they had good enough data quality. And normally we do the validation for several years, and then you would see every year separately, and then the period is summarizing them. But here we use just 1 year, so they are the same. And then you see here in the upper right plot the bias based on the season. So there we see this well-known pattern already. And so you can also see how many stations have been used per season. And there we can also see that during winter and autumn, less stations have been used, which is because of, most of the time, worse data quality of the eddy covariance station during winter. And then you can here see also an example for such a time series plot, which helps to indicate if there's a good alignment of the seasonal cycle, for example. And with this, I want to summarize the second part. So we adapted the Landwehr package for surface heat fluxes, and mainly we adapted the pre-processing of the fluxes and added some new nameless parameters for the time conversion, and also the plots and the HTML output has been adapted. And we did some example validations for the hydrological forecasting system versus ERA 5, and also for ERA 5 land versus ERA 5. With this, thank you. And also thanks for the organization and also the opportunity to do a pre-recording, because unfortunately I couldn't attend. Thank you.